All right, so let's move on and talk about alkanes. And alkanes are a class of hydrocarbon, aren't they? Right? So alkanes contain only carbon and hydrogen. But what's interesting about alkanes is that they have a general or generic formula of CnH2n plus 2. Okay, where n has to be some kind of integer, right? It has to be the number of carbons in a molecule. So let's say, for example, we had alkane that had 6 carbons in it. How would we figure out the number of hydrogens? Well, if I have H 2 times 6, 2 times 6 plus 2, that means it's going to be C6. 2 times 6 is 12 plus 2 is 14. So C6H14. Right, let me ask you guys a question. What if I had C9? Can anybody tell me how many hydrogens I would have if I had 9 carbons?
20.
Absolutely. Right, I'd have 20. Okay, so again, alkanes are saturated hydrocarbons. I'm repeating that from earlier this evening. They contain only carbon and hydrogen, and the only bonds that you can have in an alkane are carbon-carbon bonds and carbon-hydrogen bonds. And another thing is that they're what? They're non-polar bonds, okay? So there we go. I'm kind of doing some repetition here. Again, the reason that we call alkanes saturated hydrocarbons is because they have the maximum number of bonds for every carbon. There are no double bonds, no single bonds, no rings either in a saturated hydrocarbon. Well, before we move on and we look at alkenes and alkynes, let's talk a little bit about the types of formulas that we use in organic chemistry. Organic chemists are, I'm not going to say lazy, I will say organic chemists like to do the maximum amount of work for the minimum amount of effort. There you go. That's a politically correct way of saying it, okay? So that's a nice way of saying, organic chemists love to come up with all kinds of ways to express things quickly and accurately, so they don't have to waste a lot of time. And so the first way that we can represent a compound in organic chemistry is a molecular formula. But the problem with a molecular formula is that it simply lists the kind and the number of each type of atom in the molecule, but it doesn't tell you anything about the way the atoms are bonded together, right? Just like I showed you earlier this evening, I said that if you have C6H2O, right, there's 2 different ways for me to connect those atoms together to make 2 different molecules. So if I just said, hey, could you pass me the C2H6O? You'd say, what do you mean? Do you want the ethanol or do you want the dimethyl ether? So you have to be more specific. How do we get more specific than a molecular formula? One way to do that is with a structural formula. If you look at the structural formulas that are shown here, you probably recognize these as Lewis structures. What a structural formula does is it shows each atom and each bond in a molecule. Every bond is drawn explicitly in a structural formula. Now, if you have a molecule like this one that I'm circling down here on the bottom right, that's propane, the same propane that is found in a propane barbecue tank. If you look at that molecule, you might think, hey, that's not too bad. I could draw all those carbons and hydrogens. But what if I had, as we just discussed, what if you had C9H20? Then you've got a lot of carbon-carbon and a lot of carbon-hydrogen bonds to draw. And so you might be wondering, is there an easier way? Well, the answer is yes. There's a couple of easier ways. The first one is to use a condensed formula. Okay? If you think about the structures that were on the last page, we had this one, CH3, CH3. This is called ethane. So instead of writing out all the carbon-hydrogen bonds explicitly, what you do in a condensed formula is that you eliminate the carbon-hydrogen bonds, okay? And you show all the atoms in sequential order, indicating which atoms are bonded to which. So basically, we're just condensing all of these carbon-hydrogen bonds, we're leaving them out. So instead of this big structure here, we just write CH3 bound to another CH3. So that's a faster way to represent that molecule. Another example, if we had the propane molecule that I showed you earlier, or on the last slide, right? You have 3 carbons bound together. Okay, you have 2 CH3s, 1 on each end, but in the middle, the carbon is bound to 2 hydrogens, right? You have a CH2 here. And so The condensed formula reads CH3, CH2, and then CH3. And you can see already how that's much faster than writing out a complete structural formula. Now there's an even faster way than a condensed formula, and that is to use a line formula. Sometimes you'll hear Mr. Dion call that a bond line formula, okay? It's just what I learned when I was an undergraduate, so, you know, it's kind of stuck with me. A bond line formula or a line formula, again, they mean the same thing. Let's read the definition, okay? I'm going to read it directly off the slide. It says, a line formula, you assume that there's a carbon atom at any location where lines intersect. Each carbon in the structure is bonded to the correct number of hydrogen atoms. So not only do we assume that there's a carbon at any location where lines intersect, there are also carbons, and we'll put and at the end of a line. Okay, so you ready to have your mind blown in a good way? See this molecule right here, ethane? Here's my structural formula. Here's my condensed formula, and here's the line formula. It's just, and you're like, that's just a dash, man. That's right. Because I said that the end of a line represents a carbon. So that means this is the end of a line, that represents a carbon, and that represents a carbon. There's also another big assumption we make. We assume that each carbon is bound to the correct number of hydrogens. The carbon here on the end, and this one too, but let's just focus on the one on the left, it's only got one bond attached to it, this bond right here. So that means how many bonds must it have to hydrogen? It's got to have 3 bonds to hydrogen, right? It's got to have 1, 2, 3 bonds to hydrogen. The same thing applies to this carbon. It's only got that one bond, so it must have 3 bonds to hydrogen. Give me a thumbs up if you follow me on the bond line structure of ethane. Does anybody follow me? Good, great. Well, if you look at propane, it's CH3, CH2, CH3. Remember, the end of every line represents a carbon. So this is a carbon, this is a carbon. And whenever they intersect, that represents a carbon. Now, every carbon has to have 4 bonds. So let's fill it up. This carbon has to have 1, 2, 3 bonds to hydrogen. This carbon has to have 1, 2 bonds to hydrogen. And this carbon has to have 1, 2, 3 bonds to hydrogen, like that. And that's a bond line formula. So you can see how bond line formulas are extremely powerful, because you can communicate so much information so quickly with other scientists. Well, let's move on from there and talk about the first 10 continuous chain alkanes. You have to have this table memorized also. And the reason why is because it comes up in every single class that we're going to do from here until May 11th, pretty much. You're going to be dealing with the first 10 alkanes. So again, alkanes have the generic formula, CnH2n plus 2. So I have CH4, C2H6, C3H8, so on and so forth. And you need to know all the way from 1 carbon all the way up to 10 carbons, okay? So starting with 1 carbon, you have methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and decane. The first 3, methane, ethane, and propane, you just kind of have to memorize those. I guess butane would fall in there too. Pentane, if you think about a pentagram, it has 5 sides, or a pentagon. If you think about a hexagon, it has 6 sides, so hex makes sense. Hept, well, in French, the number 7 is sept, like that. So that's kind of how I remember that one. Oct, like an octopus or an octagon, has 8 sides. Non kind of sounds like the number 9. And dec, well, everybody knows what a decade is, so that's 10. And so you can kind of use those prefixes to help you remember those. Okay, now, again, you have to memorize methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and decane. You need to know how many carbons, and if you know the generic formula here, then you'll know how many hydrogens are in each one of these hydrocarbons and these straight chain alkanes. Now, I just want to, let's take a look at one of them specifically. Okay, let's take a look at hexane. And I just picked it at random. Oops, that's not a very good straight line, is it? There we go. Okay, if I look at hexane, C6H14, I could have drawn that as a structural formula showing every bond, but you can see it's much faster to draw a condensed formula like this. Now you see it says or, and you can probably tell what they've done here, but I'm going to explain it. Is what they've done is you see how there's all just CH2s right here. 1, 2, 3, 4 CH2s. So what they did is they condensed them even more inside a bracket and they put a subscript 4. Let me show you how I would draw a hexane using a bond line structure. The way that you would do it is like this. You would start by touching your pen to the paper. You see that dot that I just made? Okay, this dot represents the first carbon. Okay, so again, your pen touches the page. There's carbon 1, 2, 3, 4, 5, 6. That is the structure of hexane as a bond line structure. Now you might be wondering, why did you go up like that, Mr. Dion? Could you have gone down? Could you have drawn it like this? 1, 2, 3, 4, 5, 6. The answer is absolutely yes. Okay, but let's say we had to draw decane. Decane has 10 carbons and 22 hydrogens. If you had to draw the structural formula, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you had to fill in every single hydrogen. You see how long this is taking me? I don't even want to finish that. I'm going to erase it. But look, if I want to draw the bond line structure of decane, all I have to do is this 1, 2, 3, 4. Oops. Let me do it at the top where I can actually. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Done. Okay? So give me a thumbs up if you like bond line structures and think, hey, that's pretty powerful. I could really, sink my teeth into that. Something I could really use. A good bond line structure. All right, or a line structure, as the author of our textbook calls it. All right, wonderful. Well, let's move on and take a look over here. So here's just some examples. They're showing a molecule here. So this molecule is called isooctane. You don't have to have that memorized right now, but isooctane is 2,2,4-trimethylpentane. This is actually used as the standard for the combustion ranking of gasoline. So I think that 2,2,4-trimethylpentane is, the most efficient burning octane of all. And then the other isomers of octane don't burn as well as this one. Anyhow, so if you ever wondered where octane rating, it has something to do with isooctane. Anyhow, here is the bond line structure of isooctane at the top. Now, if I asked you to draw a structural formula for this, well, how would you do that? Well, you'd say, I know that there's a carbon at the end of every line and at every intersection. So look, here's the end of a line, here's the end of a line, here's the end, here's an end, here's an end. Where are there intersections? There's an intersection here, there's another one here, and there's another one here. And look, if it's an octane, it must have 8 carbons. Look, 1, 2, 3, 4, 5, 6, 7, 8. So that's perfect. And that's what somebody did right here. They decided to draw all 8 of those carbons out. They didn't make the bond angles exactly the same. And then they said, okay, well, this carbon over here only has 1 bond, so it's going to need 1, 2, 3 hydrogens. They said, this carbon here has 4 bonds to carbon. It needs no hydrogens. They said, this carbon here has 2 bonds to carbon, so it needs 1, 2 hydrogens, so on and so forth. And so that is how we go from a bond line structure to a structural formula. This one here is just an exercise and kind of observation of how you would condense a really big structural formula. If we look at it, we can see that on the far left, we have a CH3 right here, okay? Then it's attached to this carbon, which has 2 CH3s, right? There's one on the top and there's one on the bottom. So they took those 2 and they put a subscript 2. After that, you have a CH2, which is right here. Then you have a CH here, which is bound to 2 CH3s. You have one here. I should do it in a different color. One here and then you have 1 here. And if you're wondering, like, hey, Mr. Dion, this is going pretty fast. How do I do this? Well, what would be the best course of action would be to start working some practice problems immediately, right? As soon as you get out of class. All right, let's take a look at this slide here, which shows the tetrahedral carbon atom. So this is something that you want to have remembered from Introduction to Chemistry 1, is that a carbon is tetrahedral when it has 4 single bonds. And the reason why my voice is farther away is because I'm grabbing my model kit to bring it over here and make a model of carbon with 4 bonds. Could anybody tell me, unmute their mic and tell me what the bond angle is in the tetrahedron? Does anybody remember that from Introduction to Chemistry 1? What's the bond angle in a tetrahedron?
Is that 109.5?
Absolutely. Organic Chemistry Radio, right? Tune it in. Okay, 109. You're listening to 109.5. All hydrocarbon talk all the time. Okay? Anyhow, I'm just building a little molecular model here for you. And I'll stop presenting so I can show it to you quickly. Where are we? All right. So here's a model that I made of a carbon with 4 bonds. Okay, where was I? There I am. So you can see carbon with 4 bonds, and each one of these angles is 109.5 degrees. Okay, all the carbons are spread out perfectly equally. Now, if you're wondering, how would I represent this tetrahedron, this tetrahedral geometry on paper? And that's what we're looking at on that slide. Let me get back to it. The slide that shows the picture of the tetrahedron. Da, 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 da. There we go. So here we have the Lewis dot structure of methane on the far left. I don't like the way they've written it. It's kind of ugly. I would prefer to have it written like this, showing actual single bonds. Now, the tetrahedron, this is the tetrahedral shape right here. But how would we represent that 3-dimensional structure? Well, probably the easiest way is to put 3 of the atoms in the plane of the page or the screen, and then show one of the hydrogens going in the back and the other one coming out in front. And we're going to see that a lot in this class. You can also use a stick drawing like shown in D, and you can use a ball and stick model if you want. But these are the ones that we will probably use the most when we want to show the 3-dimensional geometry of a carbon, when we want to represent the tetrahedral geometry. So if we look at ethane and butane, right? Ethane was CH3, CH3, and butane was CH3, CH2, CH2, CH3. Let me just pause again here and make a quick model and show you the model. All right, so if I take my methane and I remove one of the hydrogens, and if I attach another carbon to it, okay, and then I put 3 bonds on that carbon, just give me a second here. Then I'll have an ethane molecule, CH3CH3, right? Remember methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane. After that, it goes to undecane, dodecane, tridecane. Anyhow, so here's my model of CH3CH3. Again, all of these bond angles, even the one here, that's 109.5, 109.5, all the bond angles are 109.5 in the ethane molecule. In the interest of time, since we only have about 3 minutes left, I'm not going to make a butane molecule. But when we go to the lab, we're going to actually make some models this semester, and you'll get to practice with a model kit and get to actually examine, a molecular model. In fact, I recommend buying a model kit if you really are struggling understanding, the way that molecules and atoms come together to make shapes. All right, so again, and another thing is that you can see that when the butane molecule is in its most stable, what we call conformation, you see how it actually kind of adopts a zigzag pattern like this? That is why when I drew or when I draw the bond line structure or the line structure of butane, I draw it 1, 2, 3, 4, like that. Okay, that's why we draw the zigzag pattern. That's why I didn't go 1, 2, 3, 4. Okay, I don't do that because it's not going to be as stable as when it has this zigzag pattern here. So we always draw that zigzag pattern when we can. All right, now I've already talked about isomers with you this evening, so I'm going to leave it here because we're kind of running out of time. We only have about a minute left, and I want to have some time to talk with my students before we call it a night.